The next example I want to look at is the seesaw example. Joe and Alice are sitting on opposite ends of a seesaw. The fulcrum is beneath the center of the seesaw with a length of 4 meters, so the total length is 4. Given that Joe's mass is 60 kilograms and Alice's mass is 30 kilograms, what will be the magnitude of the net torque on the seesaw when it is perfectly level? So in this situation shown here, first thing we want to do is identify our axis of rotation, and then we want to identify what forces are producing a torque. So our seesaw would be pivoting around the fulcrum here. So this is our axis of rotation. And if we look at our picture, we have two additional forces being applied to this seesaw. We have Joe's weight, and it's labeled, it's pointing down on the left end here, and then we have Alice's weight pointing down on the right end. And so what we want to do is we want to find the torque produced by each of these forces individually, and then recall that net torque just means the sum of all the torques on our seesaw. So torque we know is RF sine theta. And in this case, the force, for both Joe and Alice, we're looking at their weights. So the force is mg, the weight of each of them individually. So if we want to calculate the torque for Alice, I'll say TA or tau A. We're going to do R, the distance between the axis of rotation to Alice's weight, her weight, so MAG, and then sine theta. All right, so that will give us the torque due to Alice's weight. We know a lot of this information. R is 2 meters, right? So from the axis of rotation to where Alice's weight is acting, her mass was 30 kilograms, so 30, G is our 9.8, and then sine, well in this case too, our force is straight down, and R is pointing horizontal. That is not straightening out for me. And so the angle between right and down is of course 90 degrees, it's perpendicular. So when we multiply this out, we get the torque from Alice's weight is 588 Newton meters. It's worth noting what direction this is in. So her weight, if we just looked at it, would be causing the seesaw to rotate clockwise. All right, we're going to repeat this for Joe. I think I'll use the left-hand side here. So the torque from Joe's weight, I guess I'll just use a J. So R, again, this is his distance from the axis of rotation times Joe's weight, MJG, sine theta. So his distance is also 2. His mass was 60, G's 9.8. And again, his weight is also perpendicular to the lever arm, so sine 90. And multiplying this out, we get 1176, so 1176 Newton meters. And the direction that Joe's weight would cause our seesaw to rotate would be counterclockwise. I hope I said Alice's right. Hers would be clockwise. All right. So those are opposite directions. So when we find the net torque, we just have to keep in mind what direction each is pointing. So we can use the convention. We'll say counterclockwise is positive. That means that Joe's torque is positive, but Alice's torque is negative. So we'll have 1176 minus 588. And our solution to this is 588 Newton meters. That is the net torque on the seesaw. And then because we get a positive number here, that tells us the direction of the net torque is also in the counterclockwise direction. And so we do have this unbalanced torque going here.